Welcome back to this simple tutorial on creating the OWL ontologies using Protege. And in this part 2, I will be basically demonstrating the actual making of OWL ontologies using Protege. So this is the Protege, and once you open up the Protege, this is the view by default which you get. Let's just start creating the classes and then the object properties. I hope you can recall all the steps from part 1. So this is the classes tab, and by default you get certain tabs. In case you don't see all these tabs, you can go to window, click on this tabs over here and then select whatever tabs you want to see. And also it might be possible first the very first time when you install you don't see all these tabs, but you will eventually install them. You can install them and get them plugged in into your Protege version. So not taking much more time, let me create all the classes which I want, and I will use a tool called create class hierarchy because I want to create my classes and subclasses. And for that, using this create class hierarchy is very efficient. So you just need to provide all your classes and subclasses in a tabbed manner, and then click on continue and click on finish. Over here you would notice that there is a checkbox which is by default checked, and it says do you want to make sibling classes disjoint. So by default I will keep it a yes, because I want to create sibling classes as disjoint, but some of them won't be disjoint in some manner because uh, by disjoint, I hope you understand what disjoint means. If not, disjoint basically means that if there are two classes, two sibling classes, or the classes at the same level, and there are individuals or objects being instances of any of these. So there could be two cases. An individual is a member of both of these, or it can be a member of either of one. So in case if you want to specify that particular assertion, you need to make the classes as disjoint with each other. So by default, it creates sibling classes as disjoint. For example, over here it created cheesy pizza disjoint with all other pizzas, which is not going to be our case. So I'll just remove this particular assertion over here, and you'll see this is reflected in all of the sibling classes. Similarly for this particular fellow over here, and for all other things, the session remains valid, because if there is a member of pizza, it will not be a member of pizza base for sure. Similarly for pizza topping. I'll remove the disjoint assertions from toppings as well. So here you see a well-defined taxonomy, or the subclass and class hierarchy is created, and the domain, which is actually explaining my domain of pizza. So there is a country class, then there is a food class, pizza is subclass of food, then pizza base is at the same level of pizza. Under pizza we have different classes: cheesy pizza, interesting pizza, and certain named pizzas, and then pizza topping. And in the value partition, which is kind of a design pattern, I have just specified three kind of spiciness which can be added to the toppings. So let's just go to the second step, which is in this case is going to define the object property. I hope you can recall what object property means. And before going to this particular definition, let me just or let's just first create the object properties and then go back to the slide. So I'll again use the object property hierarchy from the drop down under tools and create my object properties. So I hope you remember object properties are the binary relations which basically relates to individuals. And over here you could notice that by default it is not checked. So by default sibling properties are not specified as disjoint, which is okay in our case as well. And I hope you remember in the same step we wanted to define these properties, or define the characteristics of these properties. So before that, let's just spend a few minutes to understand what are the properties of or the characteristics of object properties. So you could see there are seven characteristics, or there could be seven kinds of object properties. What are these? So if we say that if a property is functional for a given individual, there can be at most one individual that is related to the individual via the property. And functional property thus are also known as single valued properties and also features. So for example, in the picture over here, you could see if I have a object property has birth mother, and if I relate gene with the and if that is defined as functional, and if I relate gene with two individuals, Peggy and Margaret, with the same property, then reasoner will make it out reasoning that both of the names Peggy and Margaret are of the same individual, because has birth mother of can be related to one only one individual at once. And inverse functional is basically uh, it's a property is inverse functional, then it means that the inverse property is functional. That means for a given individual, there can be at most one individual related to that individual via the property, as seen in the picture as well. Then the third one is the if a property is transitive and the property relates individual A to individual B and also individual B to individual C, then we can infer that individual A is related to individual C via property B, which is also depicted in this picture in terms of has and sister property. And it also implies that it cannot be functional. So because you are going to end up in having a chain. Then the fourth property or kind is symmetric. And it says that if a property of P is symmetric and the property relates individual A to individual B, then individual B is also related to individual A via property P. And property P is said to be reflexive when the property must relate A to itself. For example, we have a property nose over here. So if that is reflexive, then that means that the same property can be related to individual again. But irreflexive is just opposite of it. For example, in this picture, is mother of is a irreflexive property by which we imply that Alice cannot be mother of herself. So these are the seven kind of properties or characteristics. Let's go back, and before that, just one more important thing, that properties link individuals from the domain to individuals from the range. For example, in our pizza ontology, we'll see the property has topping would probably link individuals belonging to class pizza to individuals belonging to class of pizza topping. So this is the significance of domain and range. And it is not necessary to define all these characteristics, but just to define all these in a minimal sense. So let's just define all of these wherever we feel the need. For has country of origin, let's just leave it as it is and let's see what will happen. For has ingredient, we say that the has ingredient is a transitive property. It has domain range uh, from the food class to and the range from the food itself, because we are going to have individuals from both of these related to each other via this property has ingredient. Then we say that has base. So has base is going to be functional because for a pizza there can only be one pizza base, and we know that it is going to be from pizza, it is going to relate individuals from pizza class to individuals from pizza base. So that is for sure, and that's why we define all those uh, definitions where we are so sure about the definitions. In case of hash topping, it is kind of a inverse functional relationship because we know that there could be many toppings on one pizza. So, but the still the range and the domain will remain the same, similar. So domain in this case is going to be pizza only and ranges would be pizza topping. So there could be multiple individuals from, you know, uh, pizza topping uh, related to pizza. And if you would have noticed, you can use control space to complete the kind of a autofill feature in case you want to do so. Similarly, in case of hash specialness, we define it as functional and we just specify the range because under the food right now we have pizza, but there could be multiple variety of food as well. So right now we just define spiciness, and if I press control space, it will auto complete it. So that's all. All of our object properties are now well defined. Let's go back to the classes. Before that, in my classes, I'll be using certain countries, and that will be kind of individuals or the instances. So let me just define certain countries over here, and I'll just define America, Italy, and say any other country, say Germany, and we'll see how I'm going to use them in my domain. So I'll just specify that these are all are of country type. So there is a class by the name country, and I'm giving them the type country. You can also use the class hierarchy from this place and then specify or just select and press enter. Similarly over here. So now let's go back to the classes and describe our classes. Now we are going to describe the classes, and this is one of the most important tasks. In the country, what I'm going to do is that I'm going to make it an enumerated class because I want to limit my choices of countries. I want to say that I'll be having countries only from this particular collection. So how would I do that? How would I create a enumerated class? By using this equivalent to description over here, and I say that country is either equivalent to domain thing, and it is going to have only from a list of individuals from only from this list. So if I say I'm going to have either America, Italy, or Germany, so this is the only list which I am going to support under the country collection, and that's it. So this is my enumerated class where wherever I am going to use country, it is only from these three countries only. That's what I mean over here. Now let's just specify or describe all other classes. Food, we will leave this as it is. In pizza, we make a general assertion and which says that pizza is going to have some pizza base, and this is the necessary condition. So we say that pizza uh, is going to have has base and some pizza base. So this is the necessary condition which I want to give to any individual who is going to be the member of pizza base. In case of cheesy pizza, I want to say that cheesy pizza is going to be any pizza and who has topping some cheesy topping. So this is my necessary and sufficient condition. What are the necessary and sufficient condition? Let's go back to the slide and explain this a bit. So from this place, you can ensure that necessary conditions are those conditions uh, which basically specifies, or with the necessary conditions alone, we cannot say that if something fulfills these conditions, then it must be a member of this class. What does that mean? That means that if an individual is a member of name class, then it must specify the conditions. However, vice versa is not true. So if some individual satisfies these conditions, we cannot say that it is a member of named class. So because it is not a sufficient condition. To make it sufficient, you need to define sufficient conditions or to make it implicit in the both directions. So if an individual is a member of named class, then it must satisfy the condition, and vice versa is also true. If a member satisfies all those conditions, then it is a member of the named class as well. And that's what we are doing over here. In Protege, if you want to define certain necessary and sufficient conditions, you need to define those under equivalent to. In case you want to define only the necessary conditions, you need to define under subclass of. And with this, it also turns your class into the primitive or the defined class, from primitive to defined class. So now the class is defined, and you could see that there is an indicator change over here. There are three horizontal arrows for all the defined classes. So we are going to have our defined classes for all these kind of pizzas. So over here I say that pizza and has topping minimum 3. So this is going to be my interesting pizza, where I'm saying that any pizza is interesting if it is a pizza and it has at least 3 toppings with it. And you could notice that for all the sub classes of pizza, this is an anonymous ancestor which is inherited from pizza. For named pizza, we won't define anything. And in the same manner, we will define, say, the named pizzas. Say, for example, if I call out any pizza in my menu as American, so what are the properties or what are the necessary conditions that make any member be the part of American pizza? So let's just define those as well. So I'll just use this class expression editor once again, and I say that any member would should have say has country of origin, uh, and its value should be America. So this is one assertion which I would like to give, or the condition, the necessary condition. Next would be say it should have hash topping, and should have say mozzarella toppings, and then it should have say another topping, say uh, pepperoni sausage topping, and uh, tomato topping. So we have say a classification in which we say that our American pizza is a pizza which has all these toppings and is has the country of origin from America. So these are necessary conditions, but there is something more to it. And what is that? We also need to specify a closure axiom. What does that mean? It's something like we just mentioned that any pizza who has country of origin America and some mozzarella topping, some pepperoni sausage topping, and some tomato topping is an American pizza. But we never said that only it can only have toppings from these three sets. So that's the universal quantification. So if you read about quantifications, and I'll just go back to the slide. Uh, so there are two types of quantifications. One is existential, and the other one is the universal. So with a closure axiom, we basically defined a kind of a universal quantification. So what does that closure axiom means? A closure axiom on a property consists of a universal restriction that acts along the property to say that it can only be filled by specified fillers. So this means that it can only has topping from mozzarella or pepperoni or tomato toppings. No other toppings can be there. The restriction has a filter that is the union of the fillers that occur in the existential restrictions for the property. And that's why if we want to do some kind of this kind of explicit definition, this becomes necessary. Now in Protege, there is one cool shortcut to define this. You just need to select all those existential restrictions on based on which you want to build your universal restriction. Select them and right click to it, and then click on create closure axiom. And that's it. The job is done. Protege has created has topping only mozzarella topping or pepperoni sausage topping or tomato topping by itself. And that's it. We don't need to define anything else for American pizza. This again, if you remember, comes from the pizza itself, from the pizza class, and is inherited to the lowest member of sub-level and further sub-level. So this is American is a kind of second level for this, and this is inherited over here as well. Now let's just define or describe Margherita pizza as well. Over here we say that we don't specify that it has some any kind of country assertions. We just said that it has some topping from tomato topping, and it also has say some topping from say we give it as a mozzarella topping because margherita is in true sense or classic sense has to has mozzarella topping. That's why we just mentioned it. And again, we want to define a closure axiom or we want to put a universal restriction on it. So we'll create a closure axiom. And that's it. We have just to make it simple, I'm not going to further classify any pizza bases. Let's just be there. So we just have a common pizza base, and that's why there's just one class. On the pizza topping, though, I have classified in cheese topping, in meat topping, and vegetable topping, and mozzarella, pepperoni, tomato are part of it. So we don't have any specific say conditions to it. Just say we can describe saying that mozzarella topping has say country of origin from um, Italy. If I am not wrong, it is from that place only in true sense. And then we add spiciness to it. So if you remember, we have defined value partition, and in that section we define the spiciness with certain collection of values. So here we define spiciness, and we say that it has some say we just want some say mild spiciness in it. So we say it has mild spiciness. Similarly, for pepperoni sausage topping, we say that we just say that it has a say spiciness, say medium, and for tomato also we say that it has spiciness, say medium, and that's it. So all our definitions are now done. Yes, I hope so. All are done, except one thing, and which is on this front, spiciness. So I want to make it, I want to give it a cover. I want to give it a cover axiom. And what is that? Let's go back to our slide to have the description on it. So a covering axiom consists of two parts, the class that is being covered and the classes that form the covering. So in a layman, let's just see these two charts over here. So just assume, or you can see that spiciness is the bigger circle, and then we have subclasses mild, medium, and hot, and there could be individuals. Now, if we don't define any covering axiom, so there could be individuals belonging to these three subclasses as well as the spiciness class itself, right? But if we want to say that any individual can be the part of either of these three only, then we need to provide a covering axiom in the spiciness uh, class itself. And after we do so, the scenario could be something like this. So any individual would be the part of either mild, medium, or hot. And basically, these three subclasses covers the whole spiciness class. And how do we do so? We just need to do a necessary and sufficient condition. We say that either it is equal to hot or say medium, or we say mild. So what we are saying basically is that any individual which belongs to spiciness can be the member of hot or medium or mild. And we do not need to specify anything in these classes, except that these are disjoint with the other ones. And that's it. So we are not done with all our descriptions. If you can recall in the part one, the step afterwards was to invoke the reasoner and check the consistency. So now let's invoke the reasoner. Go to the reasoner tab and here select the reasoners. So in your installation might be you might have different list of reasoners. Again, these can be obtained or added on using the plugins available. So I basically prefer Hermit user, which basically gives me a reasoning out of DL. And I guess they are also using first order logic based reasoning. And then I just click on start reasoner. So as soon as I click on start reasoner, it doesn't show me anything over here, right? But if I click on this particular tab over here in the asserted, I get a drop down saying asserted and inferred. If I click on inferred, I get this kind of a view. Let me just stop the reasoner for a being and just see if we have anything in inferred view. We don't have nothing, or it shows as well nothing. If I start the reasoner once again, so if I start the reasoner once again, say for example right now, I get the whole view, and this is the reasoning which basically reasoner does. So if we just see what kind of reasoning reasoner did, And if you just go to the cheesy pizza or this section, you would see the reasoner has classified or reasoned out that uh, the American and Margherita both are cheesy pizza as well, though we never said so when we were asserting them. So if I go to the asserted view once again, here I never said American is or Margherita is cheesy pizza directly, but I had asserted or given some necessary conditions based on which the reasoner did the reasoning and said that American because it has mozzarella topping, that's why, which is a part of cheese topping, that's why it's cheesy pizza, and margherita as well. And in interesting, if you would have noticed, we just get American because in interesting pizza we said that pizza which has minimum topping equals to 3, but we know that in margarita we just define 2 toppings. So this is how the reasoning is being carried out, and you would see everything similarly, and can create individuals, can reason out on them, and can extend the whole use case for doing kind of a AI job. One more thing before concluding the whole session, you don't need to really go to the inferred view. You could see all these kind of assertions or inferences. For instance, if I go to the object properties as well, there also you could see certain things in yellow. I hope so, in not in this place, but yes, I mean you could see whatever rows you see in yellow are the assertions or inferences reasoned out by the reasoner itself, and those are not defined explicitly by you. So for now, that was all I wanted to demonstrate, and yeah, that's all. I mean, from the how do we create OWL ontology using Protege? I just wanted to show all this information to you, and in case of any comments, in case of any feedback, please leave that in the comment section. I hope this particular session made some sense and was helpful you for you to get at least basics of Protege and OWL ontology. Thank you again. Thanks for watching. Thanks.